Hi and welcome back to Teardown Hardware. In this video I will talk about bipolar junction transistors, the most used semiconductor in electronic devices. Just by watching this video you are using billions of transistors, no matter if that's a smartphone, a PC or a smart TV. This video is for those that want to learn how transistors work, to those who are about using a transistor in their design but are not sure how to choose one. Transistors work like a switch, but not like any switch. To turn on your lights at home, you have to push a switch with your hand. This is a mechanical switch, but if you're asking Alexa to do it, then you are using an electrically controlled switch. That is definitely a transistor. Simplified, a transistor is an electronically controlled switch. Transistors are made of semiconductor material, which works as a conductor or as an insulator. This property is what makes transistors so special. The most common used material for semiconductors are silicon, germanium, and gallium arsenide. There are two types of BJT transistors, NPN and PNP. To keep this video short and simple, I will focus only on the NPN type, but the same principles apply for the PNP as well. NPN transistors consist of two negatively charged and one positively charged semiconductors. For each of the semiconductors, there is a pin connected to it, and this will be collector, base, and emitter. And the most important part of this is the connection between the negatively and positively charged semiconductors, which is called junction. All transistors consist of two junctions, and this is why they are called bipolar, which means two. It is very important to have a good understanding how junction works. As mentioned before in this video about semiconductor materials, more specifically about silicon. What makes silicon very special is its atomic structure. Its outermost orbit consists of 4 electrons, or valence electrons. From basic chemistry lessons, we know that the outermost orbit of the atomic structure is complete when there are 8 electrons in it. In this way, atomic bonds are created. Getting back to the silicon's atomic structure, we see that silicon atoms create a perfect bond with each other. But now the question is, how are electrons going to move from one part of the semiconductor to the other part of the semiconductor, while this bond is so perfect? The answer is with a little help. We have heard a lot about doping scandals in sports. Football players, fighters, runners, etc. take substances which give them more power, and they are giving their best performance. After testing, they are banned from sports because of doping. The same process is what makes silicon to conduct or isolate. One part of the semiconductor is doped. In this way, more electrons will be added in the atom's outermost orbit, making it unstable. This will be negatively charged semiconductor. The other part will be doped as well, but with different substance, which will remove electrons in the outermost orbit of the silicon's atom, leaving open holes. This is called positively charged semiconductor. To make something clear here, positively or negatively charged is only a term which defines whether silicon atom has a hole or extra electron in its outermost orbit. At this point, the silicon semiconductor is still an insulator, and it will become conductive if energy is applied to it. By connecting a battery, negative pole of the battery to the negatively charged semiconductor, and positive pole of the battery to the positively charged semiconductor. Then more electrons will be added in the semiconductor's negative part, and more holes will be added in the semiconductor's positive part. When the required energy from the semiconductor will be met, then the electrons will start to flow from the negatively charged semiconductor to the positively charged, and will reach the battery's positive potential. Now, the semiconductor will be in its conductive state. But wait, what we just saw was only one junction, and transistors have two junctions, remember? Yes, that's correct. Let's start simple and then make things more complicated. And if you have understood how one junction works, you have learned the basics about diodes, because that's how diodes work. But since we are talking only about transistors here, I will add the second junction and see what happens. We have now 3 semiconductors, of course doped. Since the beginning of this presentation, we have shown equal proportions of 3 semiconductors. This is actually not true. The semiconductor in the middle is actually smaller. An interesting fact here is that very often we hear that transistor size shrinks by factor of 2 every 2 years. The shrinking actually is highly depending on how small the semiconductor in middle can get. Let's now get back to see how transistor state changes from insulating to conductive. For that we need two signals. First is a signal we want to control, and second is the controlling signal. Connection will be as shown here. Let's add an LED to show transistor status. The first junction to become conductive is the junction between the base and emitter. The electrons here will start to flow from the emitter to base. Since the current that could flow through the base is very small due to high resistance, and because collector is connected to the positive potential, the electrons will be attracted from the positive potential and will start to flow from the emitter to collector as well, but with less resistance, which means current will be higher. Let's name these currents. The current flowing from emitter to base is called IBE, and current flowing from the emitter to collector is called ICE. Before going to numbers, I will make a small important information break. We have learned at the beginning what bipolar junction means, but what does transistor means? And here I'm going to explain that too. We all know transistors have two states, on and off, but that's not correct. There is a third state called active state, at which the transistor acts like a resistor. This is where the name is coming from, transfer over resistor. Let's get back to numbers and relations between the transistor characteristics again. The required voltage to change transistor state is defined from VBE characteristic, which is equal or higher than 0.7 volt. And the relation between the base voltage and collector voltage is that collector should be at least 0.7 volt higher than the base voltage. If this is clear, then we know how to change the transistor state on and off. But what about third state, which is called active state? The active state is defined by the relation between the base emitter current and collector emitter current. Here is where the beta factor plays its role. The relation here goes as follows. Collector emitter current is equal to the base emitter current multiplied with beta factor. With all this information, I'm going to the next step and show you a simulation of how transistor works in real application and what you have to know before choosing one. For the simulation, I'm going to use LT-Spice. LT-Spice is a free simulation software provided from Analog Devices. I will start by opening LT-Spice and I will create a new schematic. I will go to the components and find the NPN transistor. I will add a resistor at the transistor base to control the current flowing through the base. The ground is important for the simulation. Your simulation won't run without it. Now we need voltage sources. One voltage source we need for the base, and the next we need it for the collector. Now let's connect everything together. The voltage at the collector I will set it at 5 volts, and the voltage at the base I will set it at 1.8 volts. The R I will calculate it later on, and I will now choose one transistor. I will right click on the transistor and pick a new transistor. Now I'm going to choose some random transistor from the transistor list. I see this transistor has 100 mA collector current. I will choose that one and I will copy the part number. I will open my browser, enter transistor name and click on Mauser. I will open the datasheet and jump directly at the typical performance characteristics. Here is the base emitter voltage in relation with collector current. We see from here that the transistor active region is from about 580 millivolts up to 800 millivolts, or from 0.58 volts to 0.8 volts. I will now go in my desktop and create a calculation spreadsheet here. I will name it transistor calculation. Open it and set the parameters that we need to calculate the resistor value. The resistor value, we need to calculate it in order to limit the current flowing through the base of the transistor. By setting this current, we can then control the current flowing from the transistor's collector to the emitter. So we need the saturation voltage of the transistor, which is VB 0.8 volts. The voltage at the base, which is VB, we have set it at 1.8 volt from the voltage source. And now we need to check in the datasheet the base current relation with the collector current. This will be I base. I will open the datasheet again, and this is what we need to look at. We see here, we can set the current that can flow through the collector by setting the current at the transistor's base. Let's get the 200 microampere here. 200 microampere. Now, since this is in microampere, I will set here 1 million. Help us to make the calculations. And now, what is to be calculated is the RB. RB now will be equal to the base voltage, which is 1.8 volt, minus the saturation voltage, which is lost at the diode of the transistor, divided, this is the Ohm's law, by the current, and this we need to divide it by 1 million because it's in microampere. And this will give us a resistor value of 5000 or 5K. I'm going to open the simulation tool and set this at 5K. I will now run the simulation and measure the voltage at the base to see if that's as much as we want to set it. So this is about 205 microampere. Let's now see the current at the collector of the transistor. This is about 47 milliampere. I will jump again at the datasheet and see at 200 microampere and collector voltage 5 volts, we have about 47 milliampere, as much as the datasheet says. With all this, now you can set the current at the transistor collector as much as you like. Let's check another value, probably the maximum value given here. It's 400 microamperes. I will open my spreadsheet and set this here to 400 microamperes. And the resistor value will drop by half. I will go at my simulation again, change this resistor value to 2.5K and run the simulation again. The current is almost double. It's 78 milliampere. This is the current at the collector, but let's see if the current at the base is 400 microampere, as much as we want to set it. Yes, that's 400 microampere. And let's compare this with the datasheet. We have set the base current at 400 microampere and we have collector voltage of 5 volts. So this is around 80 milliamperes. This is actually as much as the datasheet specifies it. I hope that you find this video useful, and if you did, please like and subscribe. Thank you and see you next time.